Greetings, this is Kim Southworth from Environmental Health and Safety. We would first like to start by thanking you for attending this briefing and taking the time to watch this module. In this training module, we will talk about safety culture and its impact on universities, especially laboratories. We will discuss some of the challenges in implementation moving forward and give a brief introduction to laboratory safety programs. As we are discussing a safety culture, we will elaborate on affecting change, the differences with risk cultures, some recent laboratory incidents at other universities, and finally, some best business practices. First, we must define what is a safety culture. As you can see, there are many definitions, but they all share the same theme. That is the attitudes, beliefs, and perceptions shared by a group that they use to define their norms and the values for which they hold to their work. It determines how they will act and react in certain situations. A true safety culture requires a commitment from all levels. Basically, when you look at your safety culture, if you want to know what your safety culture is like, it really is how your people act when they believe no one is watching them. As with most things in life, there are traits and behaviors that are common for all types of various cultures. This is even true when it comes to workplaces and companies that have good safety cultures. So since we have traits and cultures and common traits, the NRC has come up with a list of what they believe are the 9 common traits that all agencies share that typically have a good safety culture. And when you look at those are leaders demonstrate a commitment to safety in their decision and their behaviors. There's a problem identification and resolution process. All individuals take personal responsibility for safety. That means at all levels. The process of planning and controlling work activities is implemented so that safety is maintained. There's continuous learning. You make the environment positive, not punitive for raising safety concerns. You have effective communications both up and down so that way safety concerns can be brought up or processes and changes can be brought down. You have a respectful work environment, and the one that I like the most is a questioning attitude. That doesn't mean that a person is defiant and not doing what they're told, but that means that a person is willing to do what is right and that they have trust in their leadership to move forward and bring issues up. When it comes to safety culture in an academic setting, we are obligated to protect the health and safety of our students and employees. The public trusts us to do this and expects it. When we are given money or money is donated towards research, they assume we are performing all these tasks safely and compliant with standards and regulations. If we were not, or if they assumed we were not, money would never be donated and research would not be accomplished. So it's important that we try to do our work as safely as possible. Just like you see a list that has common traits on what makes up a good safety culture, there are common traits which have been identified that show that you may be working or having a weak safety culture. And when you look through this list, it should look somewhat familiar to you and just kind of opposite of our other listing. So there's no clear commitment to having a safety program on all levels. The leadership may be weak in this, or that the individuals under them just do not feel they need to follow it. There's failure to establish accountability. If no one is accountable for the tasks that you have, nothing gets done. There could be a lack of interest, or weak or a missing system to track or manage your safety. A failure to educate personnel. If they're not educated, they don't know what they need to do or what's expected of them. Failure to evaluate to see if the changes that you are doing or implementing are actually working. A failure to build or maintain a strong safety culture to show that there's interest and that people have the awareness. And a big one is failure to learn from our past incidents or mistakes. If we don't learn from what has happened or a near miss that could have happened, we'll never grow or overcome any of those. Now that we know what makes a good and a weak safety culture, let's review some recommendations on how we can make our academic setting have a strong and positive safety culture. First, we need to establish lines of authority for safety. Develop a policy that includes all of our laboratory safety and includes the responsibilities to each person. Encourage every leader to become a proponent of safety and safety education. If we can get our leaders on board, it's easier to get the people under them and the students to follow along. Establish a strong and effective management system to track our safety and our safety program. Implement a hazard analysis approach in each laboratory, especially where we do research. Include safety education and training for all of our students, and that's something that you're doing here now, so it's a very good start. Adopt a credo of the safety ethic. It needs to be more than just words. It needs to be something that people actually live by, support, and put into daily actions. Establish and maintain an incident reporting system. The university already has an incident reporting system when it comes to employee injuries, incidents, and things like that. We just need to make sure we're using them and promoting and putting forth the information so it can be used by the university. Establish an internal review process of incidents and corrections so that you know what happened, you're learning from it, and that changes have been made so it's not going to happen again. I personally like this model. I think it's a great way that shows you how all the areas need to work together to work as a common goal to make safety culture positive and strong. So when you look at this wheel, we need to have the values of accountability, communication, trust, transparency, our leadership, and student involvement. All of those needs to work with our procedures of having the proper training, an inspection system, record keeping, incident reporting, safety committees working together, disposing of our waste, planning, and risk assessments. So when all of this works together, our management and employees show that they are committed to safety and they're all working together for a common goal. In this one we see, it's John Cotter. He is showing what he shows as his 8 steps to a successful change. Change can be difficult. It's not easy. So here are his goals and his suggestions on how we can make change and make it a success. He says we need to establish a sense of urgency, create a guiding coalition so everyone works together, make sure everybody shares the same vision so they're working towards the same point. To do this, we need to communicate the vision, and then we need to empower our people to be able to act on the vision. If they don't have the authority or the power to make changes happen, change won't happen. Create short-term wins so people know that things are working. Consolidate and build so we work on our gains, and institutionalize the change. So we started at small steps, showing people what needed to be, gave them the vision, and then implemented the changes. Now we saw that there was 8 steps in that change, but change can be difficult, and it's not simply developing plans or guidelines. You need to be able to get people to see the value in what you're doing and make them feel that they are part of a team and know that everyone is committed. Employees need to know that it's more than just words, that there is true feeling behind this and that we really stand behind and want to make the change. Change takes time and will not happen overnight. Some recent studies show that it can actually take up to 9 years to fully implement a change. But always keep in mind, people are watching you. Your students, especially if you're a PI, everyone is looking at you. So if you really want change to happen, you need to be behind it and lead by example. So if PPE is needed in a laboratory, you need to wear it, because if they see you're not wearing it, they won't wear it, because they will not see the value or need in it. Since change can take some time, you don't want people to think that it's not working or nor that it is worth their effort. To assist with this, find some short-term wins or have milestones along the way. Be able to show them that the work they are doing is working and making a difference. Simple things as stating that you average 15 lab findings a month prior to your training, and now you're down to 5, shows that there was some value and things were taking place. Getting people to trust in the process is important. Once this happens, you can get members to be more active and help identify problems before they happen. A near-miss program is a great tool for this. This is something that we are really working on to develop for the entire university. It just gives people a way to identify problems and show near misses before they become a huge problem. Now that we know what a safety culture is, some of the traits of a good and weak one, some tips on changing our academic setting, we will now hear from Dr. Rowland on risk cultures and an overview of a few recent accidents at other universities.
Hello, I'm Dr. Brad Rowland, and like many of you, I was not born and raised in a safety culture, but I was a convert to it. So anyway, let's discuss a little bit about the converse of that, which is a danger culture. The idea and the concepts of a danger culture and a safety culture was coined in the 1990s after a series of incidents. Now let's stop and think. Nobody would say that they are part of a danger culture. However, a lot of the attitudes and actions that are made, that are part of that culture, will inherently take risk. For instance, in Bhopal, India, over 3,700 people were killed by methyl isocyanide release. In this facility, they actually had good engineering controls. They had procedures. They had 4 points that they could have stopped this incident. And then even at the very last, they could have quenched the reaction that released the chemicals that released the toxins onto the city. However, in that situation, the senior management made decisions to switch off a major fail-safe system. Also, there was a huge lack of maintenance and a disregard for procedures as the incidents occurred. Not only that, the operators didn't trust their gauges because most of their gauges were inoperable. At Chernobyl, the reactor itself had inherent flaws to where the operation was a balancing act between the pump that supplied the water and the reactor that generated the power. It was a 2-human loop servo. But even on top of that, they had fail-safe procedures that a 27-year-old junior operator didn't follow before a safety test. The reactor was actually was not set within parameters, was a dangerous setting before they even went to the test. And at this point, the senior leadership was gone. If they would have had senior leadership there, Chernobyl would not have happened. So it's incidents like this that has led Ari Rip to study and to determine there's 2 types of cultures within the risk culture, which is the danger and safety culture. Now, like a safety culture or any culture, cultures are complex. Most of it, and in there, I mean, if you think about your own experiences, a lot of us have experiences to where we've had incidences and accidents in a laboratory, as well as near misses that we can all talk about. But let's think about a danger culture a little bit and just pay a little look at the picture there. If you think about danger culture and you think about what drew a lot of us to science, particularly chemistry, it's alluring. The parts of the danger culture are alluring. If you ever do chemistry demonstrations in front of children, they're interested in color changes and a lot of other chemical reactions, but it's always the pyrophorics and small-scale explosives that get them interested in the subject. This slide is a wonderful slide, and it summarizes the difference between the safety culture and danger culture very well. And I tend to think of it as like in the safety culture, you have incidences to where you have unplanned events that results in injury and property damage, but there's a process and there's a system in place. You believe you can do a root cause analysis and completely eliminate that type of incident from occurring again. If not completely eliminate it, greatly reduce the probability of that happening. In a danger culture, you lack these systems, you lack these processes. There's always the feeling that you have an accident that seems unavoidable. And these unavoidable type incidents or accidents will result in injury, property damage, or death. There's many similarities between a good safety system and if anybody has any experience with quality systems such as ISO 9000, there's a lot of similarities between the two. Well, when we start talking about danger culture and accidents, there's always examples. And we got 4 examples here to discuss as far as laboratories. And in the picture, this came from the University of Minnesota. And from the University of Minnesota, this was an explosion, obviously. But what happened here is that they actually had safe protocol, procedures, knowledgeable people. But what happened as research went on and they started needing more and more materials, they started changing their procedures and expanding it. They started having SOP or procedure creep to the point it was actually dangerous. And and resulted, fortunately, in no injuries or accidents, but it did result in an explosion. And then Texas Tech, we actually got a video on the Texas Tech accident. And that one, from a chemist's point of view, really spoke to me because I saw many of the lapses there I have seen throughout my career.
In January 2010, 2 graduate students at Texas Tech University were conducting research on energetic or explosive compounds, funded by the U.S. Department of Homeland Security. The students were tasked with synthesizing and performing tests on a new compound, a derivative of nickel hydrazine perchlorate. Initially, the compound was made in small batches of less than 300 milligrams. But the 2 students were concerned about potential variability among different small batches of the compound, which could affect later test results. So they decided to scale up the synthesis to make a single batch of approximately 10 grams, enough for all of their testing. They believed that keeping the solid compound wet with the solvent would keep it from exploding. After producing the larger batch, the more senior graduate student observed that it contained clumps that he believed needed to be broken up prior to testing. While wearing safety goggles, he transferred half of the new compound into a mortar, covered the compound with a solvent, and used a pestle to gently break up the clumps. After some time, he took his goggles off and walked away. A short time later, he decided to stir the compound once again. He did not replace his goggles. As the pestle pressed against the compound, it detonated. The graduate student was seriously injured, his left hand severely damaged by the force of the explosion, causing the loss of 3 fingers, perforation of his eye, and cuts and burns to other parts of his body. Post-accident photos and video show extensive damage as the explosion fractured the lab bench, shattered bottles, and sprayed the lab with projectiles. Professor Dominic Casadante was head of the Texas Tech Chemistry Department at the time of the accident.
From my perspective as department chair, you go through the emotional trauma. Oh my gosh, somebody that I know has gotten very seriously hurt, to soul searching. Why did this happen?
With these academic incidents, people like to focus on the immediate actions of the individual involved and try to poke holes and with hindsight, assert some sort of blame on the incident, on the individual involved. And what we have to recognize is that there are bigger systems at play here that can influence safety.
The CSB investigation at Texas Tech found deficiencies in each layer of safety management within the institution. These included insufficient safety accountability and oversight by the principal investigators, the chemistry department, and the university's administration. And according to investigators, there were also important gaps beyond the university itself.
I think that the way we were a year and a half ago is pretty representative of the way that a lot of universities, especially chemistry departments, are around the country. The main lesson I would really like, and it's the way that I start a lot of my talks on safety, is there but for the grace of God go you. That is to say, your universities.
The victim at Texas Tech had been working on the energetic materials project for about a year at the time of the accident. But the CSB found that he did not receive any specific formal training on working with potentially explosive compounds. The 2 principal investigators believed they had verbally established a 100 milligram limit on the production of energetic materials. But the CSB investigation found there was no formal system for communicating this limit or verifying compliance. None of the lab researchers believed that a strict 100 milligram limit existed.
When graduate students go into these new endeavors, a new project, a new process, they need to get specific training, and they need to have it ensured and have it assessed. Do they really understand what it is they're doing?
And the CSB found that the use of personal protective equipment within Texas Tech laboratories was not consistently enforced.
When we were at TTU, we learned that many people made the decision whether or not to wear their personal protective equipment based on the level of danger they felt that they were about to undertake.
There's a lot of momentum here for safety consciousness on campus, but it shouldn't have had to come to that. Don't wait for a serious accident to happen on your campus to begin to think about safety and transform your own culture.
When we think about the role of principal investigators and senior campus administrators in lab safety programs, I have concerns because in many places I feel they are not providing the leadership in this that's needed.
Dr. James Kaufman is the president of the Laboratory Safety Institute, a nonprofit organization which provides safety training for universities.
Academic institutions encourage their students to achieve excellence in their work. They need to apply that same high standard to their laboratory safety programs, environmental health and safety programs.
To achieve a high safety standard, the CSB investigation identified key laboratory safety lessons for universities. Ensure that research-specific hazards are evaluated and then controlled by developing specific written protocols and training. Expand existing laboratory safety plans to address the physical hazards of chemicals. Ensure that safety personnel report directly to a university official who has the authority to oversee research laboratories and implement safety improvements. Document and communicate all laboratory near misses and incidents.
You know, I have a PhD in physical chemistry, and I have a lab safety story. I could pull together many friends and we could sit in a room and share our lab safety stories. That should make us stop and ask these stories that we can share, those of us who've gone through the graduate program, you know, are those just stories or are those really opportunities to ensure that nobody dies again or nobody is seriously injured again, at least to the best of our abilities?
Exploring the unknown, doing research, always involves risks. Those risks are worth taking. We know that as a society. And as a society, we owe it to ourselves to do them in the most efficacious and safe ways we can.
Again, for Texas Tech, you had an experienced graduate student, but just a momentary lapse of PPE, procedure creep, and a lack of communication. It's these simple things that can add up to become a tragedy. And upon further study of Texas Tech's accident, they came up with, or they determined it looked much like a Swiss cheese model, to where the emphasis and focus on safety started from regulations through the funding sources all the way through to the student that was doing the reaction on the bench top. However, remember, a lot of the safety and safety culture is what you do when nobody else is looking. That momentary lapse could occur regardless of what requirements or the programs there. It's the decisions that's made on a small scale. Other incidents that occurred are at UCLA, Northwestern, and Dartmouth.
I'd like people to remember that Sherry was 23 years old the day she went to work at UCLA for the last time, that she was a young girl living her life to the fullest.
She really, really wanted to make a difference in the world. She really wanted to change it.
Sheharbano Sanji, Sherry to her friends, was employed as a laboratory research assistant at the University of California, Los Angeles. She had just received her bachelor's degree in chemistry and was applying to law schools. On December 29, 2008, Ms. Sanji was transferring a highly reactive chemical when some of it sprayed onto her hands and synthetic sweater and spontaneously ignited. Sherry's older sister, Naveen Sanji, now a surgical resident at Harvard, recalls the day of the accident.
When my phone rang unexpectedly and I saw that Sherry was calling me, I thought she was calling to tell me about another law school that she'd heard from. And it turned out to be a social worker from the UCLA Medical Center who told me what happened, and I was in shock. She had deep third-degree burns to over 40% of her body.
Sherry Sanji died from her injuries 18 days after the laboratory accident.
There was a life ahead that she was really looking forward to that was cut short by what happened to her at UCLA.
On December 29, 2008, when most of the campus was closed for holiday vacation, Sherry Sanji was working on a research project at the UCLA Chemistry Department. According to a report by California State OSHA, Ms. Sanji was using a syringe to transfer a solution of tertiary butyl lithium, a dangerous pyrophoric chemical that ignites spontaneously on contact with air.
Somehow, the plunger came out of the syringe barrel. The chemical was exposed to air. It caught on fire. She also had an open flask of a flammable solvent in the hood where she was working. She knocked that over. That caught fire as well.
Chemist Dr. Jillian Kemsley reported extensively about the UCLA accident for Chemical and Engineering News, using documents obtained under California open records laws.
My reaction to the news of Sherry's death was just shock. And I think pretty much the entire chemistry community was shocked.
California OSHA cited UCLA's chemistry department for failing to require appropriate body protection for laboratory workers handling pyrophoric materials. An internal UCLA safety inspection of the same laboratory just 2 months prior to the accident found that personal protective equipment was not fully utilized by laboratory personnel. Yet on the day of the accident, Ms. Sanji had neither a flame-resistant lab coat nor the much more extensive protective clothing recommended by manufacturers of pyrophoric chemicals. Dr. Kemsley believes that even a flame-resistant lab coat would have helped.
The flame-resistant lab coat would have given more time to react. It would have slowed the progress of the fire, and probably would have meant that her injuries were less severe.
And though the university said it provided adequate safety training for workers, California OSHA found no documented evidence of this.
This accident has affected the campus in a profound way, from my office to the PIs, to the chancellor and the upper administration. And we all recognized that we had to make some changes to our program to further strengthen it.
Dr. James Gibson, director of UCLA's Environment, Health, and Safety Office, says UCLA has taken steps to improve safety accountability and oversight, improve training, provide proper protective equipment, conduct unannounced safety inspections, and improve laboratory safety culture.
It's not going to happen overnight. That is something that's going to be a multiple-year process to really change the safety culture to where we think we should be.
And Dr. Gibson urges other universities to take steps to improve their education, training, and safety culture.
Once we get people to do that, we're going to see a dramatic decrease in the number of accidents that occur.
One of our main aims is to try and make sure that this doesn't happen again and that no one has to go through what we went through.
A lost life is not just an anonymous loss of life, but real people and families are profoundly affected. Safety has to be an absolute priority and the first priority for any laboratory.
Obviously, the loss of life is tragic, but an update on the UCLA is in the November 3rd, 2014 CNE News. They had an update on this event, and the University of California paid $4.5 million to an outside law firms to defend itself and the chemistry professor from felony charges of the labor code violations relating to the death of. So there are legal ramifications, on top of the obvious tragedy.
In August 1996, acclaimed Professor Karen Wetterhahn was conducting research on the biological impacts of heavy metals in her lab at Dartmouth College. She was working with small amounts of a highly toxic compound called dimethylmercury. She used a mechanical pipetting device to transfer the liquid compound while wearing latex rubber gloves. During this process, she later told colleagues, 1 or 2 drops landed on her gloved left hand. Dr. John Wynn is a professor of chemistry at Dartmouth College, where he has worked for almost 30 years. At the time of Karen Wetterhahn's accident, he was chair of the chemistry department.
She was not aware that she was in any peril at the time. She cleaned up the accident, disposed of her gloves properly. Everything had been carried out in a appropriate fume hood in her laboratory, and that was that. The spill was not considered by her significant enough to report. She was in no danger as far as she knew.
At the time, Professor Wynn said, no one in the department knew that dimethylmercury could seep through the latex rubber gloves worn by Professor Wetterhahn. But 5 months later, in January 1997, she began to show serious neurologic symptoms as her balance, gait, and speech deteriorated rapidly. Despite medical treatment for heavy metal poisoning, 3 weeks later she became unresponsive and died in June 1997, 10 months after the accident.
I think we were all stunned, not only that it was Karen, a very careful and capable researcher, but to find that such a seemingly innocuous event could have led to what ultimately was Karen's death was just unimaginably shocking.
According to Dartmouth officials, Professor Wetterhahn had consulted the material safety data sheet for dimethylmercury, which advised the use of latex rubber gloves when handling the material. Professor Wynn says the tragedy led the university to emphasize the need for comprehensive hazard evaluations, rather than relying exclusively on the safety precautions from chemical suppliers.
There was an increase in that sort of safety instruction in the sense that it expanded into things that we had not realized required such care and detail, such as glove material. The fact that she was doing something any of us would have done in terms of the care she took to transfer this small amount of material was, for all of us, the wake-up call, the signal event that says, whenever confronted with a material known to be toxic at whatever level, whether super toxic as this one was or not, we must be diligent, learn all we can from as many experts as we can about the nature of the hazard and about the protections that can be taken to handle it safely.
Material compatibilities are always a concern in selected PPEs, and they're not uncommon to find incompatibilities. They looked into UCLA, Northwestern, and Dartmouth, and after that, there were critical values that they observed between each of these, and these are, management, commitment, communications, and trust. Management, well, as the top bullet says, it is the most critical. I mean, you will always know what your management and your research thinks and what they think is important. It's almost like you can innately tell. But this is the importance that they express by either a lack of interest, lack of accountability, or tepid support for safety programs. And all initiatives are doomed if the leadership and the management doesn't support it. In the cases of UCLA, Northwestern, Dartmouth, in each of these, after the events, their management has improved, and the support within management for safety has improved. Communications, both internal and external. Internal communications, that's the backbone of safety. Being able to communicate and identify hazards, train workers, and have safe procedures are universal and paramount for employee safety regardless of industry. Now, external communications, that builds your culture, it builds your awareness, it builds reputation. I mean, even things like the number of days without incidents. I've worked in places that were by the nature of the work, were high-risk environments, and I quietly took pride in the fact that we could make 300, 600, or however many days without any sort of accident or incident. I thought that was wonderful. Also, industrial service companies, they market their incident rates because a good incident rate will convey to customers that a lower insurance, lower litigation risk. Communication did improve over all three universities. And employees and students' involvement is very important, particularly in things like near misses. They are on the work site and in laboratories. They're there every day and see safety events that are not always reported. Capturing these events, near misses or not, it provides a critical information needed to correctly modify a safety process and eliminate risk factors before they become significant. There are approximately 100 near misses for every one injury, and employee involvement in the near miss program can significantly reduce injury frequency, in some cases over 90%. Also, communications are key to build trust, which brings us to trust. Now, I mentioned before that I was a convert to a safety culture, and I've not always been it. Now, that's not to say I was unsafe or even particularly dangerous, or not in my own mind. I used to work with chemical warfare agents, both my hands-on, but later on managing people in the laboratory who did testing with chemical warfare agents. So there was very little to no room for error without somebody getting injured. And I was very confident. I've never had any injuries, never really had hardly any near misses. And when they started implementing concepts of a safety culture where I was at, yeah, I was a little resistant because I didn't know how much this guy knew about what we did for a living. But over time, after interacting both contentiously at first, but over time, we built trust with my safety officer, and not only did he make the processes in our laboratory safer, he also improved the product that we were producing because he became very intimate with what we were doing, and the relationship built to where we could actually call each other on events or things that were going on in the laboratory, resolve potential risk in a very expedited and a safer manner. But at this point, it took time. Kim earlier alluded to it takes time for safety cultures to be implemented, and that happens, and trust is key. And communication is important because that builds trust. Trust assessment for the universities involved, they improved. One thing I thought was neat was that many of these universities, they started making a mentoring program that paired PIs, researchers with students as a way of building a relationship between, if you will, management and employees. A hazard analysis also helps to build a strong safety culture. I mean, you've got to have ability to identify your hazards in your operation, determine the severity of those hazards, determine how you're going to mitigate it, and the effects of those mitigations and how well those mitigations work once they're implemented. These types of processes are necessary in order to build safe processes in a safety culture. And now Ms. Kim Southworth will come and talk about laboratory safety.
Okay, in this last section, we are just going to briefly discuss an overview of what laboratory safety program is and what it entails. This is a very broad explanation. First, we need to know what a laboratory is. A laboratory is simply a room that is designed for a special purpose or set up in a specific way to be able to perform experimentation, observation, or practices in an academic discipline. Now, when you look at a laboratory, the things you do inside of a laboratory also go along with and transfer out to when you're doing field research or you're working in the field. You don't just ignore everything you learned in the laboratory when you go out into the field. You still need to maintain safety and protect people even when you're out doing field research. When you look at a laboratory safety program, it's broken down into basically 5 major elements: the hazard identification, the chemical hygiene plan, information and training, exposure monitoring, and medical consultation and examination. Element 1, hazard identification. As you can see, it's the first step and I believe one of the most important ones. You need to know what you are working with and the hazards, because if you don't know these hazards, you will not know how to protect yourself. So hazards can come in many forms. You can see the examples. It can be chemical, occupational safety, biological, laser, radiological, fire, life, and safety. It can be electrical, it can be ergonomics, and it can be even a crushing hazard. So they can come in many different forms, and they all depend on the laboratory and the type of research and the processes that are being performed there. Not one laboratory is the same as everybody else. When you look at a chemical hygiene plan, the chemical hygiene plan, of course, applies mostly to the chemical laboratory. So if you're a computer lab or other types of labs like that, you may not need a chemical hygiene plan, but it is a major portion of anyone that has chemicals. And a chemical hygiene plan is basically the program that covers a chemical from purchasing to disposal. The members need to know how to handle the chemical, what hazards the chemicals present, and how to protect themselves from the chemical. So it basically covers everything about that material, so the person knows how it comes into the laboratory, how it's stored, how it's labeled, how it's used, and how it's disposed of. A simple way of looking at it is that the plan actually describes the cradle to grave for every material in the laboratory. And everyone should know where this plan is and what's inside the plan, or they will not know how to protect themselves or the procedures for that specific laboratory. As we said, each laboratory has specific hazards. Based on that, there's specific training and information that needs to be provided. All training that's given needs to be site-specific. People need to know how to act, perform, and all the procedures for that very specific laboratory that they're in. This could be hazard communication, emergency procedures, waste disposal, or personal protective equipment. The bottom line is everyone needs to know the procedures for that laboratory to be able to keep themselves safe and protected. The next element is our exposure monitoring. Once hazards are identified, they either must be addressed or monitored. This is done by conducting a simple job hazard analysis. This is basically taking what you do, the processes and procedures, breaking them down into steps so you can identify the hazards per step and that the process is easily understood by all. When we're looking at controlling our hazard, our first method we want to look at are engineering controls, and this can consist of our ventilation systems like our fume hoods or lab hoods that currently are in most laboratories. Just like each hazard has its unique training, each one also may have its unique medical consultation or examination. Here are just some basic ones that are most frequently used here at OSU. We have people on the IACUC and IBC programs, so they require specific training through doctors and immunizations. We have some that are on our OSHA program, which requires specific physicals from a doctor, and again, certain immunizations that can involve like hearing conservation or people on our respiratory protection program. And another one that is widely used on OSU is our bloodborne pathogen program. This one again has very specific immunizations that people require if they are exposed to certain agents or pathogens. Throughout this module, we wanted to introduce you to safety culture and its impact on an academic setting. We discussed the challenges of implementation in relevant contexts, and lastly provided a brief outline for the laboratory safety program. I would also like to take this opportunity and give you some background on EHS. In addition to the laboratory safety program, EHS also provides assistance with fire protection engineering, life safety and emergency preparedness, environmental compliance, occupational safety, occupational health and medical surveillance, materials management, industrial hygiene, and safety training here at OSU. Our contact information is provided on this slide. Please do not hesitate to contact us if there are any additional questions or concerns related to any of these programs. Once again, we thank you for your time and your attention.